In section 6.2, we are going to be learning how to calculate the area of a region between two curves. In Calculus 1, we learned that a definite integral will calculate the area underneath a curve, and that area will always go down to the x-axis if we're integrating with respect to x, or we could also integrate horizontally with respect to y, and our region would go all the way to the y-axis. So let's start with a quick little review of Calculus 1, just what we learned about definite integrals in Calculus 1. So if we were to ask to integrate from a to b f of x dx, and we'll just assume that f of x is always positive on this region, what this is going to give us, so if this is our f of x and our a to b, what this is going to give us is the area between f of x and the x-axis. Because we're doing this with respect to x, it is always going to be between f of x and the x-axis. And because f of x is above the x-axis, it's going to give us an area, and it's going to be a positive area. We could also work out this problem with respect to y. So we could integrate from c to d some g of y dy, and we'll see in this section that there are some cases where this is going to be more beneficial, and it's going to make the problem easier for us. So for example, if this is our g of x, and here's c, and here's d, if we're integrating with respect to y, that means we're finding the area between our g of y and the y-axis. So we're connecting that graph to the y-axis, and we're finding the area. And again, because g of y is to the right of the y-axis, it's going to give us a positive answer, and it's going to be a positive area. But what if we don't want to go all the way to the coordinate axis? What if we want another function to be our bottom boundary, and we want to stop that area before the axis? And we could have that bottom boundary actually be a curve. And it's actually really simple to calculate, and that's what we cover here in section 6.2. So you should have definitely seen this first part in Calculus 1 where we integrate with respect to x. But we have another option here where we can do it horizontally with respect to y. So one way that I always remember the difference here is we draw lines through the region, and I'm integrating this one with respect to x, which means it's going to be towards the x-axis. And this one I'm integrating with respect to y, which means my area is going to be between my graph and the y-axis. I'm doing it horizontally. So the new part that we're going to add is, what if we want our bottom boundary to not be a coordinate axis? What if we want to find the area between f of x and g of x? So I've got some f of x up here, and say some g of x down here. From a to b. So I'm going to show you first on how this formula is developed, and hopefully that'll make a little bit more sense and it will be easier to remember. So back to the Calculus 1 concept, if we just do the area under f of x, so we're ignoring g for now, just the area under f of x is going to take all of this region from f all the way down to the x-axis. And that would be the integral from a to b of f of x dx. But we don't want all of that. We want G to be the bottom boundary. So technically, we want to exclude this stuff. We don't want that part to be included in our area. And that blue part, which actually now turned green when I overlapped them, that part is exactly what we would get if we integrated and found the area under the G graph. So all of this stuff, all of it, is the area under F. But then just this little bottom piece is the area under G. Well, anytime we want to exclude something or remove something or take something away in math, we use subtraction. So we could end up with now what we have is just this yellow area that has a top boundary of F and a bottom boundary of G. If we integrate the F, subtract the G. And because these two integrals have the exact same limits of integration, the exact same boundaries A and B, we could technically put those into one integration formula and say the integral from A to B of f of x minus g of x. This formula would be, we will write it out, this gives the area of the region whose top boundary, and the top and the bottom is really important because that's going to affect the sign that we get, whether it comes out positive or negative. We always want the one that's going to give us the larger area to be first and the smaller area to be second because it's a subtraction problem. And if we're dealing with area, area should always come out positive. So we're going to do the larger area minus the smaller area. Anytime you do a larger number minus a smaller number, it should come out positive. So this will ensure that we come out with a positive number. So this formula here is going to give the area of the region whose top boundary is g of x, or excuse me, f of x, and whose bottom boundary is g of x. On the interval, x equals a to x equals b. So we always want the top one first and the bottom one second. So this is just the most basic. Of course, we're going to see a couple of variations that we're going to have to adjust a little bit and deal with and think about exactly how we're going to fix it. But this is just the most basic of how we're going to deal with this top boundary, bottom boundary problem. So let's look at just a simple example, and then we'll look at some things that can happen to make us have to adjust a little bit. We're going to find the area of the region between f of x equals x squared and g of x equals, let's say 2x. And I did not give you any x boundaries. And that happens a lot. So we're going to have to figure those out on our own. And it's really not that difficult. There's a way that you could work it out by hand, but there's also a way that we could just figure it out really quickly on the graph. You should always start by drawing this graph. That's going to help you decide which graph is the top boundary and which graph is the bottom boundary. And especially in problems like this, when they don't give us those x values, the graph is also going to help us determine those x values. So always start with a graph. So f of x equals x squared is just a basic parabola. It goes through 0, 0, 1, 1, 2, 4. And I'm only drawing the right-hand side of it, and you'll see why in just a minute. It's because of how g of x behaves. G of x equals 2x is a straight line with a slope of 2. It goes through 0, 0, and then it goes through 1, 2, and then it goes through 2, 4. So not the most beautiful graph. It's kind of hard to draw sometimes on the computer. But you will see we don't really need our two x values because these two graphs just kind of naturally pinch off this little area here in our first quadrant. And that's why I only drew the first quadrant part. Obviously, if you didn't know that was going to happen, you could go ahead and draw the other side of your parabola. And we drew the other piece of our g of x function that goes on to quadrant 3. And we see that nothing's really happening over there. They don't really have the area between them that gets pinched off like the piece that does in quadrant number 1. So now that we have this piece here in quadrant 1 that gets enclosed by our two graphs, we can tell which one's on top and which one's on bottom. And we can also tell the x coordinates where this region starts and where this region ends. So just from the graph, I can see that they have x equals 0 in common, and they have x equals 2 in common as well. So this region's going from x equals 0 to x equals 2. So we're going to be integrating from 0 to 2. And then we want everything under that g of x graph. G of x equals 2x is our line. And once we draw it, we see that one ended up as the top function. So that one gets written first. If we were to go all the way down to the x-axis from g of x equals 2x, that one would create more area. So we want that one first. But we don't want to go all the way down to the x-axis. We want to stop that area at that parabola, f of x equals x squared. So I'm going to say exclude anything under the x squared graph. And that's what stops us at the x squared graph. So our setup is the integral from 0 to 2 of 2x minus x squared. And we're integrating with respect to x because we can draw vertical lines through this region that point down to the x-axis. And once we get it set up, the integral is really easy to calculate. It's just really understanding the graph and the region and the setup. And most of the stuff we're going to learn here in chapter 2 is this, or chapter 6 is the same way. We're mostly concerned with learning how to interpret the graphs and how to take that information and use it to set up some sort of integral. Once we do that, usually the integration part is a really integration, something very basic that we learned in Calculus 1. The integration part's not tricky at all. So this would be our area. And if we actually want to know what the area is, we would just have to find our antiderivative and plug in our limits of integration. So the antiderivative for 2x is x squared. Antiderivative for x squared is 1/3 x cubed. And we've got some limits of integration. Remember, you always plug your top boundary in first. So we're going to plug 2 in to x squared minus 1/3 x cubed. And we get 4 minus 8/3. And then we plug 0 in, and we get 0 minus 0. So we just have to figure out what 4 minus 8/3 is, and we'll have our answer, which is actually 4/3. So the area of that odd little region, which we would never be able to find with any sort of geometric formula because it's so odd-shaped, we could easily do it with calculus, is 4/3. Sometimes these regions aren't that simple. There are a couple things that could require us to make some adjustments though. The first thing is if our top boundary and our bottom boundary flip-flops somewhere in our region. If that's the case, we said that when we set up this formula, the top boundary is f of x, and it has to be f of x for that entire interval a to b. The bottom boundary is g of x, and it has to remain the bottom boundary for that entire interval a to b. So for some reason, they switch within our interval. We're going to have to set up a new definite integral. We're going to have to break our region up into two pieces. And you'll actually see once we graph this, if they do switch, the graph kind of just naturally breaks itself into two pieces anyway. So that's a good indicator that we're going to have to do this. It doesn't always do that, but it does sometimes. So we'll see. First, I'll start with just kind of a generic example so you can see what it would look like. So here's our f from a to b, and then here's our g. And we're asked to find all of the area between these graphs from a to b, all of the area. So if we connect them at a and at b, we will see that for part of the region, f is on top. For this first piece, f is on top. But then somewhere in the middle here, they switch. They've got this intersection point. Something's going on there, and they flip-flop. And then from that point on to B, they've switched, and now G is on top and F is on the bottom. So we've got this second region as well that we need the area for. If we were just to integrate from A to B and say F is always on top, G is always on bottom, this second piece would come out negative because F now is creating the smaller area and G is creating the larger area. So if we did F minus G, we would be doing smaller minus larger, and we would get a negative. And we don't want that. We want all of the area between these two functions. So if we want all of the area, we're going to have to split this into two pieces. So I'm just going to give this question mark some random label here. Let's just call it C. I know it's not alphabetical order, but we're going to call this region number 1 and region number 2. So for region number 1, we're going to have to integrate from A to C, because from A to C, f of x is on top and g of x is on bottom. And then for region number 2, we're integrating from C to B, because from C to B, g of x is on top and f of x is on bottom. So by switching the order in the subtraction, we will ensure that this will always come out positive and this will always come out positive. And then we can add them together to get a total amount of area between these two functions. So our total area would be region 1 plus region 2. So we're allowed to split apart the A to B interval as long as we don't leave anything out. So the first set of limits go from A to C. So everything from here to here. And our second set of limits go from C to B, which is everything from here to here. So we've still included everything. We've still included everything from A to B, so we've left nothing out. But we would work those integrals separately, find those areas separately, and then once we got those answers, we would add them together for our final answer. So you need to make sure that your top function stays your top function the whole entire time, and your bottom function stays your bottom function the whole entire time. And if for some reason it doesn't, then you're going to have to break apart your interval in into pieces and integrate them separately. So our next example, we're going to have to use this concept. It's not going to exactly look like the picture I just gave you, but we are going to have to use the same concept. So we're going to try to find the area of the region bounded by y equals square root of x, y equals x minus 2, and y equals 0. So we've got 3 boundaries. Usually when you have 3 boundaries, you're going to have kind of a triangular shape. This isn't going to be exactly a triangle, even though y equals x minus 2 is a straight line, y equals 0 is a straight line. Y equals square root x is not a straight line, it's a curve. So it's going to be kind of triangular, except one of the sides is going to be a little bit curvy. So just like with the last one, we have to start with a graph to see where these functions are located. Again, we were not given an interval to integrate over. We just want to know all the area that's inside of these 3 functions. So we have to know what this region looks like. So you always start with a graph. If you are not sure how to quickly graph these 3 functions, you are more than welcome to use your graphing calculator to quickly graph these 3 functions and see what they look like. You could also use Desmos at www.desmos.com. This is a really nice online graphing calculator. I almost like it a little bit more. Not almost, I do like it more than our handheld TI-84s. It's a lot easier to use. So I've already got a couple of our functions in here. Let me add the third one. So we've got y equals square root x is the red graph. We've got y equals x minus 2. I put it in as negative 2 plus x, but it's the same thing. But let me put it in the way that I wrote it just so we're not confused. There we go. And they made it orange. That's fine. Doesn't matter. And then we also have y equals 0, which you can't see because y equals 0 is the exact same thing as the x-axis. So between the red graph, the orange graph, and the x-axis, we've got this little triangular type region in quadrant 1, but it's got kind of that curvy top side. With the red graph is making it have a curvy top instead of a flat top. So I'm going to transfer this over onto our notes and we'll see why exactly we've got to split this up into pieces. One thing that's also nice with Desmos, since we were not given boundaries, you can see from Desmos that the far left boundary is 0, and then the far right boundary is x equals 4. We're not worried about the y's. We're integrating with respect to x, so you just need the x values. So it's 0. The region all the way to the left is at 0, and all the way to the right is at 4. So we've got y equals square root x. We've got y equals 0, which is the x-axis. So I'm going to try to make that one a little bit darker. And then we've got y equals negative x plus 2, which crosses our x-axis at 2. And then it meets our square root graph up at 4, 2. We don't care what it does down below because it did say that we were using the x-axis as a boundary, so we're stopping at the x-axis. So this is the region we end up wanting to analyze. We don't have an issue with our top function here. So the way that you can check, like I said earlier, draw vertical lines towards the x-axis. That means I'm going to try to integrate this with respect to x. Draw arrows towards the x-axis and see where they cross first. All of our arrows are crossing y equals square root x first. So the top boundary is always y equals square root x. But then if you look and see where these arrows are pointing, for part of this region, they're pointing at the x-axis. And then for another part of this region, they're pointing at our y equals x minus 2 line. So halfway through the region, the bottom boundary changes. So we're going to have to split this region up into two pieces. We're going to have to split it there at 2, where we have this intersection point. And if you look at these two separate regions now, region number 1 always goes from square root x to 0. Region number 2 always goes from square root x to x minus 2. So now we always have one top function, one bottom function, one top function, one bottom function, but we are going to have to integrate this in two separate pieces and then add our results back together. So for our first piece, it looks like our arrows are always starting at the square root x graph and always ending at the y equals 0 graph. And that region number 1 just goes from 0 to 2. And then region number 2 always starts at the square root graph and always ends at the 2x graph. X minus 2 graph. Now you need to be careful because our bottom graph has two terms in it and we're subtracting it. So technically that subtraction is going to have to be distributed. So it's always a good idea to use parentheses here. If we didn't use parentheses, we would get the wrong answer. And that region goes from 2 to 4. So we've got two integration problems to work out. They will give us the area of these two individual portions. If we just add them back together, we'll get the area of the whole thing. Subtracting 0 for the first one doesn't do anything. We're really just integrating square root x from 0 to 2. So let's go ahead and work these out. So remember, square root x is x to the 1/2. So to integrate x to the 1/2, we're going to add to the exponent and then flip the new exponent. So our antiderivative is 2/3 x to the 3/2. And then if we plug in 2, 2 to the 3/2 is not a nice rational number. 2 cubed is 8. And then we want the square root of 8. Don't change these to a decimal. Don't just type this into the calculator. We want an exact answer. We're going to be having problems similar to this in MyLabs Plus, and almost always MyLabs Plus is going to want an exact answer. So this is 2/3 times the square root of 8. And then if we plug in 0, we just get 0. So that first one, we can simplify this a little bit. Square root 8 is 2 root 2. So this turns into 4/3 radical 2. So that's our area for region 1. Now for region 2, we're going to have to go ahead and distribute that minus so that we can work that one out. So this is the integral from 2 to 4 of square root x minus x plus 2. Now again, if you did not put that second function in parentheses, your minus there would not have turned to a plus, and you would get the wrong answer. So be generous with your parentheses. An extra set of parentheses would not hurt. So that first piece integrates the same way. We said the antiderivative for square root x is 2/3 x to the 3/2. And then the antiderivative for x is 1/2 x squared. Antiderivative for 2 is 2x. We've got our antiderivative. Now we want to evaluate So we're going to plug in 4. Always plug in your top number first, which should be your bigger number. So that 3/2 means we're going to square root it and cube it. Really doesn't matter the order that you do them in, as long as they both get done. If it doesn't work out to be a nice rational number, then we'll leave it as a radical. Do not change it to a decimal. But this one does work out nicely because 4 is a perfect square. So I'm going to go ahead and square root it first. That half part of your power means square root, remember. So the square root of 4 is 2, and then 2 cubed is 8. So this first piece ends up as 16/3. 4 squared is 16. A half of that is 8. And then 4 times 2 is 8. So that's what we get when we plug in 4. And then we're going to subtract what we get when we plug in 2. We already know when we plug 2 into this first piece, we get 4/3 radical 2, because that's exactly what we did up here. Remember, 2 cubed is 8, and then square root it. We can't square root 8, but we can simplify a little and write it as 2 root 2. So that's 4/3 root 2. And then 2 squared is 4. Half of that is 2. 2 times 2 is 4. And we'll clean this up as much as we possibly can. Those guys will cancel. We've got -2 and +4 is going to end up being a +2, but then we're subtracting it. So -2, which is, if we get it in terms of thirds, that's 6/3. So 16/3 minus 6/3 is 10/3. So that's the area for our second part of our region. And if we add these two together, the total area is region 1 plus region 2. So we've got 4/3 root 2. And 10/3 minus 4/3 root 2, which works out very nicely because those 4/3 root 2 just cancel each other out. So our total area is just 10/3. Total area just ends up being 10/3, ends up being a nice rational number. But we have to split this one into two pieces because the bottom function changed. We see that on the far left, it goes all the way to 0. On the far right, it goes all the way to 4. Even though the top function stayed the same the whole time, the bottom function did not. So at that point where the bottom function changed, we had to split this guy in half. And then we had to integrate it as two separate pieces. Anytime your top function or your bottom function changes, you've got to start a new integral. There is another option for this one, though, that it is worth checking. And we will get the answer much easier and much quicker if you're willing to try it. So we're actually going to look at this exact same problem again, and I'm going to give you one more possible variation on this problem. And it goes all the way back to why I referenced this sideway integration with the y-axis. You can integrate with respect to y, and that will give you the area between your function and the y-axis. It turns out this last problem that we just did, if we were to integrate it horizontally with respect to y, then we wouldn't have to break it into two pieces. Now I'm not going to start drawing on top of this one again. I think it's already a little bit too cluttered. We're going to draw it one more time. We're going to do the exact same problem again. But sometimes it may be easier to integrate with respect to y. And that might help you avoid having to break apart your region into pieces and integrate multiple area problems. So we're going to look at this exact same problem one more time, because this problem, if we were to look at it horizontally instead, we would not have to break it apart. So again, we're trying to find the area of the region. Between y equals square root x, y equals x minus 2, and y equals 0. Exact same three functions. We're not changing anything about this problem. We're just going to kind of change our perspective on how we look at it. And it's going to help out a lot. So I'm just going to draw the piece that we need. So remember, this went all the way to 4 at the end, and that was the point 4, 2. Now I'm labeling the entire point because when we start integrating with respect to y, our entire integral is going to have to be in terms of y. This was the point, that is 2 on the x-axis, but it's the point 2, 0, so that might be helpful. And this is 0 on the x-axis, which is the point 0, 0. So this is 2. Now we said, and I'm going to erase this here in just a second, but we said if we look at this thing horizontally or vertically, top function stays the same, but right here at 2, the bottom function changes. So we had to split it apart. So your other option, before you do all that work in splitting it apart, you might want to really quickly look at it in the other direction. So instead of drawing vertical arrows, draw horizontal arrows towards the y-axis. So since now my arrows are pointing towards the y-axis, I'm looking to see if I can integrate this with respect to y instead, if integrating with respect to y would be easier. And what we're looking for is when we draw those arrows, do all of the arrows hit the same function first and point to the same function last? And they do. All of these arrows hit our, this was our y equals x minus 2 line. Every single one of our horizontal arrows hit y equals x minus 2 first, and then they all point at y equals square root x after that. There's no change in top-bottom function. It's technically not top-bottom anymore. It's more like right and left now that we're going horizontal. So we're looking to see if it's always the same right function and left function. So if we work this problem out horizontally, we won't have to break it apart into pieces. The trick with this, though, is if we're going to work it out with respect to y, everything in the problem has got to be changed to be with respect to y. Our functions have to be rewritten in terms of y, and our limits of integration will be y values now instead of x values. So we're still working with the exact same region. The area we get should still be exactly the same, but the setup of our integral is going to look a little bit different. So y equals x minus 2, we've got to rewrite that so that it's not y as the dependent variable, x as the independent variable. We want to switch those guys around so that it's an x equals equation. We want y to be the independent variable. When I set up my integral, I want y to be the variable inside that integral. So this is really easy to solve. We just have to add the 2 over. So it's x equals y plus 2. And we've got to do the same thing here with y equals square root x. And this one's also pretty easy. We need it to say x equals something. And to solve for x, we just have to square both sides. X equals y squared. Those are the functions we're going to use if we're going to integrate this with respect to y. So our area, remember when we go from right to left, it hits the line first. So we're going to write our line first. and then it hits our square root graph second. But when we rewrote it in terms of y, it turns into y squared. And now we're not integrating 0 to 4. Those are x values. If we're going to do this horizontally, everything needs to be in terms of y. So now we're looking at the y-axis for our limits of integration. And this region on the y-axis goes from 0 to 2. Now this one is so much easier to integrate than splitting it into two pieces and dealing with those crazy radicals, square root 8 that we had to change into 2 square root 2. This is going to turn out a lot nicer. So antiderivative of y is 1/2 y squared. Antiderivative of 2 is 2y. Antiderivative of y squared is 1/3 y cubed. And then we're ready to evaluate. We're going to plug in 2. So 2 squared is 4. 1/2 of that is 2. 2 times 2 is 4. 2 cubed is 8. And we're going to multiply by 1/3, so 8/3. So that's what we get when we plug in 2. And then you plug in 0, and we're going to get 0 plus 0 minus 0, so all zeros. So we've got 6 minus 8/3. And if we rewrite 6 in terms of thirds, it's 18/3. So we've got 18/3 minus 8/3 is 10/3. So much easier. The trick is, though, to just check for that before you decide you're going to split it into pieces. Check for that really quickly. If we were to try to do this right to left instead, could we avoid having to break it apart? The only extra work you have to do is rewriting your functions as functions of y as opposed to functions of x. And then you're ready to go. Usually it's going to be a much easier problem than having to split it up into pieces.